Hello friends, now we will discuss two important topics in operational amplifier, and that again comes in linear applications, that is voltage to current converter circuit and current to voltage converter circuit. Fine. Voltage to current converter circuit is also called voltage controlled current source, that is VCS. This is called VCVS, VCIS, voltage controlled current source, VCCS you can say, and this is current to voltage converter, that is current controlled voltage source. Fine. So we will start with the first one, voltage, that is V to I converter, voltage to current converter circuit. We have three different circuits in this category, that is V to I converter. First, we will be talking about floating load converter. Fine, that is floating load converter. And second, we will be talking about grounded load converter. Fine. And in this also we have two modes, again two categories. First one is, that is you can take inverting mode, and second you can take the non-inverting mode. Fine. So these are the three different circuits we'll be talking about in V to I converter circuits. Let us start with the first one, that is floating load converter. Floating load converter is essentially the circuit like this. We have a resistance R1, we have negative feedback, then we can take load impedance here or load resistance, it is your choice, that is ZL. Fine. Then this is grounded, and we connect input to this terminal, that is non-inverting terminal, that is V in. Fine. So this is your output voltage, and rather than saying output voltage, I will not talk about output voltage here. I will be saying I have load current IL here. Fine. Load current is current through the load impedance, or that can be load resistance as well, or load resistance as well. Sometimes we denote it by RL or by ZL, that depends on the type of element here. Now voltage at node A is definitely voltage at node B in case of negative feedback ideal op-amp circuits. Fine. So here what do we have? Voltage at node A for ideal op-amp. For ideal op-amp, voltage at node A is same as voltage at node B, and that is input voltage here. Fine. This is current which will be flowing for ideal op-amp. Current entering into inverting and non-inverting terminal is always zero. So this load current will be flowing through R1 as well. So the load current IL is equal to VA upon R1, or that is load current is equal to VA is same as input voltage, so that is V upon R1. So please see carefully, my load current is independent of load impedance. By changing R1, I can vary the load current. So load current is independent of load resistance. So when load current is independent of load resistance, so we are able to convert this voltage source to current source. Fine. So that is called voltage controlled current source. So this is important. Try to remember it. You have a lot of questions based on this in objective type questions like engineering services prelims or GATE exam. Now let us talk about second case, that is grounded load. Fine. So in grounded load we will be talking about inverting mode first. Let us see the circuit. In this case I will be talking about inverting mode first, that is inverting mode. So in that case, the circuit will be similar to what we discussed. Here I have load impedance. The circuit will be like this. The circuit is like this only. We have load resistance here, that can be RL or ZL. We have a resistance connected here. We have a resistance connected here. Fine. In inverting mode, I have input applied at this terminal. We have our resistance connected here. This is grounded. Fine. This is R, this is R, this is R, this is R. All resistances in the circuit are same except load resistance, like this, right? So I have like this. Fine. So this is R. This is R, this is R, this is R, this is R. This is load. And current in this resistance is IL. Fine. Now, for ideal op-amp, remember one thing, if this op-amp is ideal, for ideal op-amp, remember this is which mode? That is inverting mode, right? Inverting mode, V to I converter. For ideal op-amp, voltage at node B is same as voltage at node A. And if this voltage is V0, if this voltage is V0, apply KCL at node A. Applying KCL at node A. What do we get? VA minus V in by R plus VA minus V0 by R, that is equal to 0. So what will be VA? VA will be equal to 1 by 2 V in plus V0. That's it. This will be the voltage at node A. Now applying KCL at node B. Fine. I have to find this current I, that's why I have applied KCL at this node first. And for ideal op-amp, voltage at node B is same as voltage at node A. Now, when you apply KCL at node B, what do we get? Current in this branch is what? That is VB minus 0 divided by R, that is outgoing current. So VB minus 0 divided by R, that is current, outgoing current in this branch. What will be current in this branch? That is IL. Fine. What will be current in this branch? That is VB minus V0 divided by R, that is equal to 0. See it carefully. I will be putting a star here. What is this resistance? This one. This resistance is this one, although this is equal to R. That's equal to R. Fine. Now, I have to find load current. So let us see how to go ahead. So this gives VB. VB is what? 1 by 2 V in plus V0. So this is 1 by 2 V in plus V0 divided by R. So divided by R, I will say R star, plus 1 by 2 V in plus V0 minus V0 whole divided by R plus IL is equal to 0. That's it. Fine. Now this gives V in divided by 2R star, that's equal to R. I'm just identifying that this is R star, plus 1 V0 by 2R star. Fine. Plus 1 by 2R into V in, and you please see this is V0 by 2, this is V0, so this will be minus V0 divided by 2R plus IL equal to 0. Now see carefully, this is, I am just saying this is R star, but that's equal to R. So this and this term is cancelled out. This and this will be added. So this gives V in upon R is equal plus IL is equal to 0, or that gives the load current. I will write here, that gives load current IL is equal to minus V in upon R. Fine. My load current is independent of load resistance. Load current is independent of load resistance, but it is function of input voltage. So that is why we call this circuit as V to I converter. So this is your output, but in inverting mode. Fine. So this is your second circuit, that is V to I converter in inverting mode. Another possibility in this case is, say this is grounded now and we connect input here. Fine. Everything is otherwise similar. So now in this case as well, the procedure will remain same. Let us see that. For ideal op amp, this is your second case. Which case? That is non-inverting mode. This is non-inverting mode. Otherwise procedure will remain same. Find voltage at this node, apply KCL, and you will get load current. Let us see that. For ideal op amp, VB is equal to VA. Apply KCL at node A. When you apply KCL at node A, so this will be VA minus 0 upon R. This voltage minus this voltage is this outgoing current. This current is 0 for ideal op amp. Current in this branch is 0 for ideal op amp. So this current will be what? VA minus V0 upon R. VA minus V0 upon R, that is equal to 0. So that gives VA equal to, you please see carefully, that is VA is equal to what? That is V0 by 2. VA is V0 by 2. Fine. So this is equation number 1. Now apply KCL at node B. Now apply KCL, this is node B. So what will be current in this branch? VB minus V in upon R. So I will not mention it R star. So VB minus V in by R is current in this branch. Fine, that is R only. Then what is current in this branch? IL. What is current in this branch? VB minus V0 upon R. That is current in this branch. Current in this branch is 0 for ideal op amp. Current entering into non-inverting terminal is 0. So this is the expression of your KCL equation, right? So what is VB? What is VB? VB is equal to VA. VB is equal to VA. Fine. So it means I can write this, I can replace this. This is equal to VB, of course. So I can replace this by V0 by 2. So we will rewrite this equation like this. Let us see that equation. So by putting VB equal to VA, and that is V0 by 2. So this equation can be rewritten like this: V0 by 2. Let us write the equation again. That is V0 by 2 minus V in by R, then plus IL. VB is what? V0 by 2. So plus V0 by 2 minus V0 by R equal to 0. And I will mention to be star. I'll mention it to be star, but that is R only. Fine. So this is what? V0 by 2R star minus V in by R star plus IL. Then what is this minus V0? So minus V0 by 2R, that is equal to 0. This and this term is same. I am saying R star, but that is R only. So this and this is cancelled out. So this gives the load current is equal to input voltage by R or R star, that is this resistance. Fine. So I can select it to be variable, but value equal to R only. Fine. So by varying this, I will be able to vary the load current, or I can say Of course, all the resistances has to be made equal, but the point here is my load current is independent of load resistance. So I am able to convert that voltage source to the current source. So that is again V2I converter, but this is in non-inverting mode, and that finishes your voltage to current converter. Fine. So there can be, in fact, there are a lot of questions based on the V2I converter. So try to remember these expressions directly if possible. Otherwise, you have to solve the circuit again and again, and this is important for all the exams, for engineering services, for civil services, mains, and for gate exam. So this is one of the important topic. Now let us see second topic, that is current to voltage converter. Current to voltage converter circuit. The current to voltage converter, that is current to voltage converter circuit, is also called current controlled voltage source. That circuit is simple. I have op-amp plus minus, this is grounded, we have a current source connected to your inverting terminal like this, and we have the load resistance connected here. I will say load resistance connected here. Fine. This is V0. This is RL. Right? So please see it carefully. What is voltage at this node? This is 0. So VB 0. So VA is definitely equal to 0. But this current entering for ideal op-amp, current entering into inverting and non-inverting terminal is 0. So this current will be flowing into this, that is IS. So if this is 0, so IS will be equal to 0 minus V0 divided by RL. 0 minus V0 divided by RL. So I am able to get output voltage, that is RL, as a function of the source current. So we will say this is current to voltage converter circuit. That is a simple circuit but important one. There can be one objective type question based on this. You don't have a repeated questions on this topic, but still you should be knowing how to implement I to V converter using operational amplifier, and of course that is inverting mode circuit only. So and that finishes your voltage to current converter and current to voltage converter. Now we will see the questions based on these topics. Hello friends, now let us see the examples based on the voltage to current and current to voltage source converters. The first example here is, in the circuit shown in the figure, the input voltage V in is given to be 2 sin 100 pi t. For RL in range of 0.5 kilo ohm to 1.5 kilo ohm, the current through RL is. So this is the circuit given to you. So you have to find current through this resistance RL, that is load resistance. Fine. So in this case the load is variable and we have to find load current. So the procedure for any op-amp circuit is, what do? We find the voltage at non-inverting terminal, which is nothing but input supply voltage, that is V in here. So the voltage at your non-inverting terminal, that is this terminal, is this input voltage. Fine. Now what will be voltage at this node? For ideal op-amp, the voltage at inverting terminal is same as voltage at non-inverting terminal. So for ideal op-amp, V minus is equal to V plus, and that is equal to your V plus voltage is input voltage. So that is nothing but 2 sin 100 pi t. Fine. So now the voltage at inverting terminal is this. Now what is current in this resistance? That is current in 1 ohm. the current in 1 ohm, that is IL, current in 1 ohm resistance is same as current in RL, because current entering into inverting and a non-inverting terminal is 0 for an ideal op amp. So, current I will be equal to your V minus the voltage at inverting terminal divided by resistance of 1 kilo ohm, and that is nothing but 2 divided by 1 kilo ohm into sine 100 pi t. Fine. That many milliamperes. Why milliamperes? Because I have written simply 1, it was 1 kilo ohm. So, it will be that many milliamperes. So, this is nothing but, this is how much? 2 sine 100 pi t, that many milliamperes, and you can see this is your answer. Fine. Now, let us see the next example. Remember, here load current is independent of load resistance. So, given circuit is floating load type voltage to current converter. Why? Because input is signal is voltage and output signal through the load resistance, that is output signal through the load resistance is current. So, we say this circuit is nothing but, that is what? This circuit is voltage to current source converter. Fine. Now, let us see the next example. In the circuit given below, op amp is ideal, the value of current IL in microamperes is, you have to find this current. Fine. Although I may be giving you the the procedure for it. Fine. But we will be writing the direct answer at later stage. So, remember one thing, voltage, how to proceed here? Find the voltage at this inverting terminal, that will be same as voltage at this terminal. Find this voltage, say this is terminal A, this is terminal B, and say this is voltage V naught. Fine. So, if you apply KCL at node A, please see, when you apply KCL at node A, fine, that gives what? VA minus 0 volt by 100 plus VA minus V naught output voltage by 100, that is in kilo ohm. So, this is equal to 0. So, this gives V naught equal to 2 VA, or we can say VA is how much? V naught by 2. That is it. Now, see carefully. For ideal op amp, we know VB is equal to VA, voltage at non-inverting terminal is same as voltage at inverting terminal, and that must be equal to what? V naught by 2. Now, apply KCL at node B. KCL at node B. When you apply KCL at node B, we get VB minus 1 volt divided by 10 plus VB minus V naught, that is current in this branch, this was current in this branch, divided by 10. Fine. I will just remove this. So, that is VB minus V naught by 10, and outgoing current again IL. I am simply applying KCL at node B. The current outgoing this way, current going this way, current going this way, sum of all must be equal to 0. Fine. And we know what is VB, that is V naught by 2. So, this is V naught by 20 minus 1 by 10 plus, you can please see, this is V naught by 2, this is minus V naught. So, it becomes minus V naught by 20 plus IL equal to 0. So, this and this gets cancelled out. So, IL will be equal to 1 by 10. That many what? That many, this was in kilo ohms, this was in kilo ohms. So, that many milliamperes. Fine. And if you talk about microamperes, so this will be 1000 by 10, that many microamperes. So, this is equal to 100 microamperes. So, this is your answer. Fine. Now, please see it carefully. What is the current? I can write current here IL equal to this resistance IL divided by input voltage by R, this resistance, you can say this is R star, that is R star. But provided these values are equal, these values are equal, that happens in that case. So this can be written 1 by 10 milliamperes directly, but you should remember the procedure rather than mugging up this formula, because these values can be different. Fine. So that is how we solve the question. So you can see the procedure, I have followed the same procedure. Now that is what we have done in the solution. Now consider the circuit again. Consider the circuit. What is the load current? So you have to find the load current here, and in this case this is non-inverting terminal. So here I have given voltage at this point, so this is in inverting mode. Previous case, in the previous example, it was in a non-inverting mode. Input was given here. Input was given at which point? At non-inverting point, and inverting point was grounded. But in this circuit, you can see it carefully please. Your inverting point is given input and this is grounded. Fine. Again procedure remains same. I can write the answer directly. IL is equal to Vn upon R star, that is this resistance R star you can take, and that is 10 by 1, that many milliamperes. 10 will be the answer, but it is inverting mode, so there has to be minus sign, there has to be minus sign, minus 10 milliamperes. So it must be answer B. But I will again say, in GATE exam, don't remember such type of formula directly, because you may be getting confused. If this and this equal, this and this equal, only then that will be applied. But I will stress on the procedure rather than mugging up the formula. This is A, this is B. Fine. So what, apply KCL at this node. So we get VA minus 10 upon 1 plus VA minus V naught by 1, that is equal to 0. So V naught will be equal to 2 VA minus 10. Then apply KCL at this node. So you get VB upon 1K plus VB minus V naught minus V naught by 1 plus IL equal to 0. But here what is VA? For ideal op-amp, I can rewrite it like this. VA is equal to 1 by 2 V naught plus 5. I can write VA, and that must be equal to VB for ideal op-amp. Remember, for ideal op-amp, voltage at inverting terminal is same as non-inverting terminal. So this is equal to VB. So I can replace this VB by this value, that is 1 by 2 V naught plus 5 plus 1 by 2 V naught plus 5 minus V naught plus IL equal to 0. And you can see carefully what I have, 1 by 2, 1 by 2. Fine. So this is 1 by 2, this is 1 by 2, this is minus V naught. So IL is equal to how much? That is 10 milliampere, but this is plus, so this has to be minus. IL is equal to minus 10 milliampere. What I mean to say is, if you follow the proper procedure of applying KCL at node A and then at node B, you can find the current. So that same procedure has been followed here. First I have obtained the voltage at node A, and then we have applied KCL at node B, and finally we could calculate your current. So shortcut, I have given you the shortcut also. Fine. Now let us see the next example. Here the value of V naught in the circuit is, that means this is a current to voltage source converter. So this 0.3 milliamperes will flow through this. Fine. This will be flowing through this, and if this is flowing through this, so you can see, first of all, this is nothing but, you can see it here, a voltage divider circuit. But voltage V naught is not voltage drop across this. Voltage V naught is drop across this as well as voltage drop across this. So this is node A, suppose this is node B. So what is VB? VB is nothing but 20 by 30 plus 20 multiplied by what? V naught. Why? Because voltage at node B is nothing but that is the fraction of this voltage. Voltage across 20 ohm is what? 20 divided by 20 plus 30 into V naught. This is called voltage divider rule. So this is 2 by 5 into V naught. Now this is VA. So what is current I? This is suppose current I. So this same current will be flowing through this, that is I. So current I will be nothing but VA minus V naught divided by 10 kilo ohm, that many milliamperes. Why? Because VA minus this voltage divided by 10 is current in this branch, and that is same current because current entering into inverting or non-inverting terminal is 0 for ideal op amp. So for ideal op amp, VA is equal to VB. So this gives I equal to VA is equal to VB means 2 by 5 V naught minus V naught divided by 10, that many milliamperes. And you know what is I? That is 0.3 milliamperes. So 0.3 is equal to this will be how much? Minus 3 by 5 into 10 into V naught. So this gives V naught how much? V naught will be equal to minus 5 volt. So this is your answer. So that is how we can solve this circuit. So solution is given to you in detail, what with the similar steps whatever we have done. Fine. Now let us see the next example. In the circuit shown in the figure, the output voltage will be, you have to find the output voltage. Here it is nothing but a current source with a resistance connected in parallel. So we can find the output voltage by simply applying KCL at this node. So if you apply KCL at this node, what do we get? VA minus 0 divided by 1 kilo ohm plus VA minus E naught divided by 100 kilo ohm, that is equal to 0. But remember, if this inverting terminal is grounded for ideal op amp, voltage if non-inverting terminal is grounded, here it is grounded, so voltage at this terminal is same as voltage at this terminal. So voltage VA will be equal to 0. If voltage VA is 0, so this is 0 minus 0, so this becomes 0, this becomes 0. So what will be E naught? E naught will be equal to I am sorry, there is one more current here, that is minus 100 microamperes, that is microamperes, that is equal to 0. This is kilo ohms, I will take it in kilo ohms, this is kilo ohms. Fine. So when VA is 0, you put it 0, you make it 0. So there are three currents basically. This is one current, this is incoming current, this is outgoing current. So VA minus E naught by 100 is this current. VA minus 0 divided by 1 kilo ohm is this current, and 100 milliampere is microampere is incoming. So this is minus 100 microampere. So this gives VA 0. So this is 0, this is 0. So what do we get? We get E naught equal to 100 microamperes multiplied by how much? This is 100 kilo ohms. So this is 100 kilo ohms. So finally you get E naught equal to, you please see it carefully, that is how much? 10 volt. So this is how you can simplify this circuit. So that has been solved in the same manner. Now let us see the next circuit. In the circuit shown in the figure, you are given this circuit. In the circuit shown in the figure, the expression of I naught upon II, that is output current by input current, is. That procedure will remain similar here. Let us see how to simplify that. So first of all, please see it carefully. This current, incoming current, will be flowing through this circuit. So voltage at this node is 0, voltage at this node will be definitely equal to 0, So VID is 0 for ideal op-amp. If it is ideal op-amp, so V naught will be equal to nothing but RF multiplied by input current I with minus sign, right? Input current I. Why? Because when current this current will be how much? I input, and this will be plus, this will be minus, this is terminal is grounded. So if it is grounded, so V naught will be equal to simply minus RF multiplied by input current. So V naught is this, and what do we need to find? We have to find the ratio of input current to output current. Now let us see what will be current in resistance R. Current in resistance R, I will be equal to how much? V naught upon R. If it is V naught upon R, so this is nothing but minus RF upon input into input current divided by R. That is what you are going to have. That is current I. So if you apply KCL at this node, so current I plus current I naught plus incoming current, so that has to be minus incoming current, that is equal to 0. Remember, this is outgoing current, this is outgoing current, and this is incoming current. So this has to be outgoing current is positive, outgoing current is positive, this is incoming current, input current, so that is equal to 0. Fine. So you know what is I? I is minus RF divided by R into I input minus I input plus I naught. So I can make equal to I naught, and I will make it plus. Fine. So what do we get? From here you will get I naught, that is current I naught, equal to, you can simplify that, or you have to find the ratio of current I naught to I input, and that will be simply RF plus R divided by R, or that is nothing but this is how you have. So this will be equal to 1 plus RF by R. So what is the answer? Answer should be C here instead of B. So there is a correction here. Fine. So this is your answer. Now let us see the next example. In the input resistance Vx upon Ix of the circuit in the figure is, you have to find the input resistance, that is nothing but ratio of Vx upon Ax. Remember, when you say input resistance, so that input resistance is nothing but input resistance for this circuit will be Vx upon Ix. You have to find this ratio. Remember the procedure. Procedure here is, what you do, you either apply KCL at this node, or you apply at KCL at this node. Fine. The procedure will be remaining same. So if you apply, what is voltage at this node, that is non-inverting terminal, so that is Vx. If it is Vx, please see it carefully, this voltage is Vx here. Fine. So voltage at this node will be equal to Vx. If it is Vx, in that case what will be V naught? V naught will be equal to, I can write directly 1 plus R2 upon R1 into Vx. This is the output voltage for non-inverting point. If you apply KCL at this node, you will get this relation, this is Vx. Fine. So by applying KCL at this node, you will get 1 plus R2 by R1 into Vx, right? So this gives how much? R2 is how much? 100. So and R1 is 10. So 1 plus 100 by 10 whole multiplied by Vx, and that is nothing but 11 Vx. Output is 11 Vx. So current here, remember, current entering into inverting as well as non-inverting terminal is 0 for ideal op-amp. So the same current will be flowing like this. So current Ix is nothing but Vx, that is voltage at this node, minus V naught divided by R3. So that is Vx minus V naught by resistance R3. So this is Vx. We have already obtained V naught in terms of Vx. So Vx minus 11 Vx upon R3, or that is minus 10 Vx upon R3. You know what is R3? R3 is given to you. So minus 10 upon 1 mega ohm. So that is 1, this will be in how much? I'm sorry. So what do we get? What will be the ratio? Ratio Vx upon Ix will be equal to minus R3 by 10. And you know what is R3? R3 is nothing but 1 mega ohm. So that is minus 10 raised to power 6 divided by 10, and this is equal to minus 100 kilo ohms. Fine. This will be your expression, that is minus 100 kilo ohms. So this is how you solve the question. So that procedure has been followed and you have obtained the expression of input resistance. Fine. So let us see the next example. Find output voltage of the circuit given below. So here we are having input two amplifiers. First I will try to find out the voltage at this point. Remember, this is grounded point, so voltage at this point will be 0. So this current of 1 milliampere will be flowing this way. So output will, voltage drop across this will be plus minus, but V01 will be minus of this. So I can write V01 equal to 1 milliampere of current multiplied by 1 kilo ohm resistance. So that is 1 volt, but with minus sign outside. Why minus? Because the voltage drop across this is plus minus, so this is minus side, so V01 will be negative. So V01 is negative, and this is input voltage to this is simple non-inverting amplifier. So V0 will be 1 plus 90 by 10 multiplied by V01. How did I write? This is RF, this is R, so this is 1 plus RF by R into V01. So that is nothing but 10 into V01. V01 is how much? Minus 1 volt from here. So this gives minus 10 volt. So output voltage for the given circuit is minus 10 volt, and that finishes your voltage to current and current to voltage converters.